Welcome to the Deep Dive. We're the show that meticulously sifts through your sources, distilling them into the most important, insightful, and sometimes pretty surprising nuggets of knowledge. Today, we're plunging into something truly foundational. It underpins almost everything in our modern world. Software engineering. When you think about the apps on your phone, maybe the smart devices in your home, or those intricate global systems managing everything from finance to critical infrastructure, well, they all rely on incredibly complex software. But beyond just knowing software is everywhere, the really profound question we're tackling is, how is all this software not just built, but crucially, how is it built with robust security baked in from the very start? So we're embarking on a deep dive into the world of traditional software engineering, specifically looking at it through the, indispensable lens of secured software development. And this isn't just about developers tapping away writing lines of code. Not at all. It's about a disciplined, rigorous, and frankly, highly structured process. It's an entire methodology, really, that ensures not only reliability and functionality, but maybe most critically in our interconnected age, ironclad security. Think of it like constructing digital fortresses, not just building blocks and doing it right from the ground up.
Exactly. And our mission for you, our listeners, is to unpack these foundational methodologies and practices, the ones that really underpin this entire traditional software engineering landscape. We'll meticulously highlight precisely how security has, transformed. It used to be a mere afterthought, sometimes just a final checkbox, right?
Wow.
But now it's become an intrinsic, interwoven component across every single thread of the development fabric. And for this exploration, we've drawn from a detailed video transcript and a comprehensive PDF. Both of them lay out the how and why of building robust, secure software in today's, let's face it, increasingly complex and threat-filled digital world.
Absolutely. So consider this deep dive your shortcut to becoming not just informed, but genuinely well-informed. You'll get the critical processes, the best practices, the stuff that's absolutely essential to prevent costly mistakes, protect sensitive data, and, ensure the integrity and trustworthiness of the software you interact with every single day. Understanding these foundations, I think, is key to truly appreciating that often invisible architecture, the one that keeps our digital world running safely and smoothly. It's a field where the unseen rigor is often way more complex and vital than what first meets the eye. Okay, so let's start by really digging into what we actually mean by software engineering. It's a term we hear a lot, but maybe it's sometimes misunderstood. When we talk about it, we're definitely talking about something far more expansive, more disciplined than just, programming. Our sources make it abundantly clear that software engineering is essentially the rigor in the software production life cycle. It's a comprehensive, systematic approach. It manages the entire process, and we're talking everything. From the very initial spark of an idea, through its meticulous design, development, rigorous testing, deployment, ongoing maintenance, even all the way to a system's eventual retirement. It's a highly structured discipline, really, aimed at creating digital solutions that are reliable, efficient, and, of course, secure. Now, what actually drives this meticulous discipline? Our sources say it's primarily business-driven. Yeah, every piece of software typically begins as a business necessity, right? Maybe a new market opportunity or an internal process that needs fixing, a critical service to deliver, or even just a customer problem to solve. This initial business need is then carefully converted step by step into actual software. So it's not just tech for tech's sake.
Exactly. It's about strategically tackling real-world business challenges and creating value.
And it's not just business goals driving it, is it? The sources also mentioned it's governed by regulatory imperatives.
Oh, absolutely. That's huge. We're talking about a whole labyrinth of laws and regulations, different regions, different rules, places where software is built and used. Think about GDPR in Europe, the General Data Protection Regulation that dictates exactly how personal data must be handled.
Right, a big one.
Or PCI DSS, the Payment Card Industry Data Security Standard. If your software touches payment card data, you have to comply. And these aren't just suggestions, they're non-negotiable legal and compliance requirements. They profoundly influence every aspect of how software must be engineered. They often impose specific security and privacy controls right from day one. Building on that crucial context, the core of traditional software engineering is typically structured around what our sources describe as an 8-step process. Now, this isn't just some loose guideline. It's a foundational, highly structured approach to creating software. It's meticulously designed to ensure consistency, quality, and predictability in a field that, let's be honest, can quickly get chaotic otherwise. Let's break down these 8 pivotal steps. And as we go through them, I want us to think about the underlying purpose and, importantly, the security implications at each stage.
Okay, sounds good. Lay it out for us.
All right, first up, Requirements engineering. This is the very first step, and arguably the most critical. It focuses entirely on understanding what to engineer. It kicks off with elicitation. That's the active process of gathering what stakeholders actually need.
So talking to people, basically.
Yes, but more than just talking. It involves deep dives through interviews, focused workshops, maybe even observing users in their environment to really get their pain points and what they want the software to do. Then comes specification. This is where all those gathered needs, both functional, like add item to cart, and non-functional, like must respond in under 2 seconds, are meticulously documented. Often in formal documents like a business requirement document, BRD, or a detailed software requirement specification, SRS. These become the North Star for the whole project.
Got it. The official plan.
Exactly. And finally, there's validation and verification. This is about making sure those documented requirements are accurate, actually feasible, unambiguous, and truly reflect what the stakeholders want and need. And here's the critical insight, especially for security. This is often where projects secretly fail.
Really? Right at the start.
Absolutely. If you get your requirements wrong here, you're not just building the wrong thing. You're often baking in fundamental security flaws from day one, flaws that will cost exponentially more to fix later. It's like building a digital house on quicksand. Security requirements, things like data privacy rules, who can access what they must be explicitly captured right here. Okay, step 2. Software design and architecture. Once you clearly understand what needs to be built, this step shifts focus to how to build it. It's about laying down the entire system's architectural boundaries, making those crucial decisions on core technologies, choosing the right design patterns.
Design patterns. Like blueprints for common problems.
Exactly. Things like the factory pattern for creating objects, the observer pattern for managing dependencies between objects, or the model view controller, MVC pattern for structuring user interfaces. Common, reusable solutions. This phase produces vital artifacts: high-level designs, HLDs, more detailed low-level designs, LLDs, data flow diagrams, DFDs, showing how information moves, and entity relationship diagrams, ERDs, for database structures.
So these are the real technical blueprints then?
Precisely. They detail everything from module interactions to data storage. And from a security perspective, this is absolutely where you design for resilience. You anticipate potential attack vectors. You integrate secure design principles from the get-go. Third, software construction. This is where the rubber meets the road, the actual building happens. Developers translate those meticulous designs into working code using the chosen programming languages and frameworks. This involves not just writing code, but also things like code generation, doing initial unit testing to check individual pieces work, and making sure everyone's following the agreed-upon code quality standards. It also includes the crucial process of building the application from all the source code and integrating the different modules together so they function as a whole. Security here means writing secure code, avoiding common pitfalls. Fourth step, software testing and verification. This is absolutely pivotal for ensuring quality and compliance. It covers both functional aspects, does it do what it's supposed to do, and non-functional ones, is it fast enough, is it secure?
So this is more than just the unit test developers do.
Oh, much more. While unit testing might start during construction, this phase expands significantly. You've got integration testing, making sure different modules play nicely together. System and acceptance testing, UAT. This is where end users actually validate the software against their original requirements. And then there are specialized tests. Automation for tests you need to run over and over. Performance testing for speed. Load testing to see how it handles heavy traffic. It's all about providing rigorous quality assurance and verifying that the software meets the requirements and the design specs. It's a critical gatekeeper for functionality, reliability, and increasingly for security vulnerabilities. Okay, step 5. Software maintenance and evolution. Software is rarely a build once, shelf forever kind of product, right?
Definitely not. Things are always changing.
Exactly. So post-launch, it needs continuous support and adaptation. This includes corrective maintenance, just fixing bugs found in production, adaptive maintenance, keeping it compatible with changing environments like a new OS version or a third-party service update. Then there's perfective maintenance, adding new features or improving performance based on feedback. And preventive maintenance, proactively refactoring code to prevent future problems and, crucially, applying security patches as new vulnerabilities are discovered. This ongoing phase keeps the software relevant, efficient, and secure over its lifetime. Step 6. Configuration and change management. This is all about managing the codebase's lifecycle efficiently, especially on big, complex projects. It involves robust version control systems, think Git or SVN, to track every single change made to the code. This lets teams collaborate without stepping on each other's toes and allows you to roll back if something goes wrong.
Essential for teamwork.
Totally. It also covers release deployment management. That's everything from creating stable builds to carefully executing rollouts to production, and critically, enabling swift rollbacks if a new release causes problems. And often, you'll have change control boards to formally review and approve significant changes, ensuring everything is controlled and documented. From a security standpoint, this makes sure only authorized, reviewed changes get into production. Almost there. Step 7. Software engineering process and project management. This step focuses on the overarching approach and governance for the whole software creation effort. It involves deciding on the right process model. Is it the rigid linear waterfall? Or more iterative approaches like the V model? Or agile methodologies like Scrum or Kanban, which prioritize flexibility and rapid feedback loops?
Big strategic decisions.
Huge. It also covers crucial stuff like planning and estimation techniques, maybe using story points in agile and critically, risk management. That's identifying, assessing, and mitigating potential project risks, including technical and security risks that could impact scope, budget, or timeline. This is where the strategic orchestration happens. And finally, Step 8. Software quality assurance and metrics management. This step formalizes quality across the entire lifecycle, making it measurable and continuously improvable. It includes various QA activities, formal audits, code reviews, walkthroughs designed to catch defects and ensure standards are met. It also involves defining and tracking key metrics. Things like defect density, how many bugs per 1,000 lines of code, or code coverage, what percentage of the code is actually exercised by tests.
Making quality tangible.
Exactly. And constantly pursuing continuous improvement, maybe aligning with industry standards like CMMI or SPICE. This continuous measurement helps identify trends, pinpoint areas for enhancement, and crucially, uncover systemic security weaknesses.
Wow, that's an incredibly comprehensive, almost, forensic structured approach.
Yeah.
It's a lot to keep track of. What's really fascinating is how the industry tries to visualize and simplify all this complexity. Our sources highlight a couple of compelling ways. First, you mentioned mind maps. These aren't just simple diagrams, right? They offer this comprehensive, interconnected view. They show how all these different aspects, risk management, use cases, agile metrics like burn down charts.
Which are super useful in Agile, by the way. They visually track work getting done over time.
Right. And testing strategies from unit tests all the way to end-to-end validation, how they all dynamically connect. They also show quality metrics, code coverage, static analysis results, different design patterns like microservices, or even identifying anti-patterns, things you shouldn't do. Plus the CI/CD tools we'll get into, code reuse, peer reviews, and those development methodologies like Scrum. It really brings it all together visually. And then there's this other one, which is quite popular and, frankly, pretty ingenious, the periodic table analogy for software engineering.
Ah, yes, I've seen that one. It's quite effective.
It really is. Just like the periodic table in chemistry organizes elements based on their properties, this analogy does the same for software engineering phases and components. Our sources describe how, requirements might be grouped in pink, design elements in orange, infrastructure stuff in blue, testing activities in green. It gives you this immediate, intuitive way to relate to and visualize all the complex, interconnected pieces.
It's a great shorthand.
Totally. It brilliantly highlights how visualization helps understanding in a field that's inherently abstract and has so many moving parts. It's more than just a clever diagram. It's a powerful way for teams to quickly grasp the scope and dependencies of a project.
Okay, so we've got that foundational 8-step process laid out. Now, it's absolutely critical to understand how these steps are actually organized, orchestrated, and, governed in the real world. Our sources group them into what they call 3 major buckets, or governance patterns. Each one represents a distinct yet interconnected layer of control over the whole process. First, you have the big overarching one, the software development lifecycle, or SDLC. This defines the holistic methodologies for managing the lifecycle of a software. Everything from its earliest concept through pre-requirement chats, detailed design, development, testing, the go-live moment, and crucially, into that extensive post-maintenance and evolution phase.
So a whole journey, cradle to grave almost.
Exactly. And the reason it's profoundly called a cycle is key. Software is fundamentally not a write once and shelf it forever product.
Right. We touched on that with maintenance.
Precisely. The digital world is dynamic. Requirements constantly change. User demands evolve like crazy. New tech emerges. Security threats adapt. This means you need continuous updates, bug fixes, performance tweaks, maybe even significant new features. The SDLC provides the essential, flexible structure for this ongoing, iterative evolution. It ensures that even as things change, there's a defined process to manage it all. Okay, the second major bucket is the build and integration cycle. You probably know it by its acronym, CI/CD.
Continuous integration and continuous deployment, right?
Oh.
Or delivery.
Exactly. Continuous integration and continuous deployment, or sometimes continuous delivery. This bucket focuses squarely on operationalizing the delivery mechanics of software. It's all about how the code, once written, is continuously integrated by multiple developers, automatically compiled into something runnable, rigorously tested, and then seamlessly deployed to various environments, dev, staging, production. It streamlines that technical flow, getting code from a developer's laptop into the hands of the end user, automating away a lot of the manual steps and potential human errors. And finally, the third bucket, operational automation, more commonly known by its portmanteau, DevOps. Now, while CI/CD focuses on the technical pipeline, DevOps promotes a deeper culture and collaboration. It's about bridging the gap between the core development teams, developers, tech leads, architects, and the operations teams.
The ops teams being the ones who manage the servers, deployment, monitoring, all that.
Exactly. They handle infrastructure provisioning, ongoing support, maintenance across all environments, from dev right through to production. DevOps is about breaking down those traditional organizational silos that often existed between dev and ops. The goal is a seamless workflow and shared governance that maximizes both speed and stability.
That's a really insightful overview of that traditional landscape and how those three pillars work together. But here's where it gets really interesting and, frankly, absolutely critical for today's world. Over the last decade or so, security hasn't just been added to these buckets. It's been fundamentally embedded, woven into the very fabric of each one. This isn't just some trend, it's become standard practice. It's non-negotiable now, transforming how software is built and maintained. And this deep integration has naturally led to some new, powerful acronyms that you hear constantly now, right?
Definitely.
The traditional software development lifecycle, SDLC, has evolved into the Secured Software Development Lifecycle, SSDLC. Security isn't just a phase, it's a pervasive concern throughout. The continuous integration and continuous deployment, CI/CD pipeline, now includes security checks at every turn. That gives us continuous integration, continuous deployment, and continuous security, CI/CD/CS. Security gates still built right into the automated flow. And DevOps, that collaboration between dev and ops, has transformed into DevSecOps. This signifies that security is now a shared, collective responsibility across the entire lifecycle, not just siloed off with a dedicated security team. And this shift, it's not just about adding more steps or throwing new tools at the problem, is it?
Not at all. It's about making security an intrinsic first-class citizen in how software is conceived, built, delivered, and operated. It's really a testament to the ever-increasing threat landscape and, all those regulatory pressures we mentioned earlier. Precisely. This whole evolution culminates in what our sources aptly call the core triangle that defines modern secure software engineering. Each point of this triangle plays a distinct yet interdependent and profoundly crucial role. They all work together. First, you have SSDLC. It defines the overarching secure framework for managing the whole lifecycle. It ensures security is considered and integrated right from the very first thought, from the initial planning meeting all the way to final decommissioning. It's kind of the what and when of security integrators.
Right, the overarching process.
Then you have DevOps, or maybe more accurately now, DevSecOps. This provides the essential principles for collaborative teamwork. It bridges those traditional gaps, maybe even that sometimes antagonistic relationship between DevOps and now security, making it a truly shared responsibility. It's the who and how of teamwork.
Breaking down the silos.
Exactly. And finally, CI/CD/CS. This offers the technology pipeline infrastructure. It acts as the indispensable catalyst that enables all these continuous processes, integration, deployment, and crucially, security to happen at speed and scale. This is the tools and the automation that makes it all feasible. This powerful triangle really forms the backbone of how secure software is built, delivered, and operated today. It's the engine that drives agility with security, not at its expense. And it sets the stage perfectly for us to dive deeper into each of these pillars. Okay, let's take that software development lifecycle, the SDLC, and really dissect its 6 major phases again. But this time, for each one, let's focus not just on its purpose, but also the concrete artifacts it produces, the measurable outcomes we track, and crucially, the key key stakeholders involved and their specific influence on security. This should really highlight how a traditional SDLC morphs into an SSDLC. Phase 1. Planning and requirement analysis. Purpose. We said this is where you deeply understand user needs, define system expectations, prioritize what needs to be built, figuring out the what. Artifacts. You'll see those requirement specification documents, FRS, SRS, BRD. Use cases, user stories, stakeholder analysis reports, maybe early wireframes. Measurable outcomes. We track requirements, completeness, clarity, stakeholder approval rates, that traceability matrix, making sure every requirement maps to later stages. And critically, initial risk identification reports. Surfacing security risks early. Stakeholders. The business team is key here. Product owner, CSO, Chief Information Security Officer, business analysts, risk officers, their security influence, absolutely critical. They align security requirements with business goals, identify compliance needs, GDPR, HEPI, PCI, DSS, and embed these into the foundation. Mess this up, and you build in security debt from day one.
So the CISO is involved right from the start now.
Ideally, yes, or at least their function is represented. Security needs to be a first-class requirement, not an afterthought. Phase 2. Design. Purpose. Knowing what to build, this defines how to build it. System architecture, modules, data flow, UI, artifacts. High-level design, HLD, low-level design, LLD, data flow diagrams, DFDs, entity relationship diagrams, ERDs, architecture diagrams, the blueprints, measurable outcomes. We assess design coverage of requirements, modularity cohesion metrics. We validate UI/UX prototypes for usability and, importantly, security implications. Stakeholders. The architecture team is central. Security architects baking in security, solutions engineers defining tech direction, data architects handling data, UX leads focusing on the user. Their influence, profound. They prevent architectural flaws, implement data protection, encryption, tokenization, ensure cryptographic standards. This is security by design in action, proactively mitigating whole classes of vulnerabilities.
So preventing problems before code is even written.
Exactly, that's the goal. Phase 3. Implementation, coding, purpose, translating design into working code. The actual construction, artifacts, source code, code repositories like Git, version control logs, build scripts, documentation, comments, API docs. Measurable outcomes. We look at code quality metrics like cyclomatic complexity, basically. How complex and potentially buggy is the code? Unit test coverage, adherence to coding standards, defect density found early, stakeholders, the development team itself, supported by DevOps engineers building pipelines, and often a designated security champion within the team. Their security influence is direct. Implement secure coding practices, often guided by OWASP Top 10. Use input validation, output encoding, enforce security gates in the pipeline. Stop insecure code early.
So the developers themselves have security responsibility now.
Increasingly, yes. Security champions help bridge the gap, but secure coding is becoming a core developer skill. Phase 4. Testing. Purpose. Verify it works, meets requirements, is bug-free. Challenge assumptions, exercise the code. Artifacts. Test plans, test cases, bug defect reports, test summary reports, automation scripts, measurable outcomes. Test coverage, defect detection rates, pass-fail rates, mean time to detect resolve defects, stakeholders. The testing team is crucial. Penetration testers simulating attacks, QA leads managing quality, project managers overseeing, auditors verifying compliance. They identify critical attack vectors, integrate security tests alongside functional ones, verify compliance controls.
So dedicated security testing is a big part of this phase.
Absolutely. Things like penetration testing become much more integrated, not just a final check. Phase 5. Deployment. Purpose. Release the software for real-world use across various environments, progressively moving towards production environments. Typically progresses from developer environments, laptops, to integration, shared server, QA testing, U8 staging, production-like for final sign-off, and finally production, live, could be cloud, on-prem, hybrid. Each gets progressively more secure.
A controlled rollout.
Very controlled. Artifacts. Release notes. Installation guides. Deployment scripts. Configuration files. Measurable outcomes. Successful deployment rate, downtime metrics, rollback frequency. How often do we have to undo a deployment? Stakeholders. The operations team is the backbone. Ops managers, IAM specialists, access control, network engineers, release managers, cloud architects engineers. Their security responsibility is immense, enforcing hardening standards, principle of least privilege, secure network configs, managing secure rollbacks. And phase 6, maintenance, purpose. Ongoing updates, fixes, optimization post-release, handling feedback, threats, and eventual retirement, artifacts. change logs, patch updates, performance reports, incident response documentation, measurable outcomes, frequency, severity of issues, mean time to recovery, MTTR, after incidents, customer satisfaction scores, update success rates, stakeholders. The development and support team wears multiple hats here. SOC analysts monitoring threats, support leads handling user issues, compliance managers ensuring ongoing adherence, executive sponsors overseeing long-term value. Their role is vital for real-time threat response, handling security requests, patching, ensuring ROI. And this phase also covers strategic decisions about retirement, re-engineering, rehosting, rebuilding, or decommissioning old apps securely.
So security is ongoing, even after launch.
Absolutely continuous, the threat landscape never sleeps.
That detailed breakdown really drives home the complexity. But now let's talk about that core philosophical shift you mentioned that defines the secure software development lifecycle, or SSDLC.
Yeah.
The shift-left philosophy.
Yeah.
You said traditional SDLC could be quite reactive, right? Security checks often late in the game, like a final audit.
Yeah, often too late, like checking the foundation after the house is built.
Whereas SSDLC flips this, it's proactive or shift-left. Security is integrated right from the absolute beginning, from that very first requirements meeting. And the benefits of doing this, you said they're substantial. What are they again?
Oh, huge. First, and maybe most compelling, cost reduction. Fixing defects, especially security ones, late in the game, say, in production is exponentially more expensive. Not just a bit more, orders of magnitude more.
The stitch-in time saves not idea.
Exactly. Detecting security flaws during requirements or design drastically cuts overall cost and rework compared to finding them in testing, or worse, after a breach. You build a foundation right the first time. Second, you get profoundly improved outcomes. Proactively addressing security issues means higher customer satisfaction and trust. A secure product isn't just a feature anymore, it's table stakes. It builds immense brand loyalty.
Especially with breaches making headlines all the time.
Precisely. Third, it significantly boosts overall project success. Our sources cited some scary numbers. ICT projects averaging 200% overruns, often due to late-stage security disasters. Shifting left mitigates these major overruns by catching problems early. This means key activities, security risk assessment, threat modeling, compliance analysis, defining abuse cases, how might an attacker misuse this, are baked into those very early planning and design phases. It sets a secure trajectory from the start.
Okay, so to make this shift left really concrete, let's see how specific security activities get woven into each SDLC phase, transforming it into a true SSDLC. Security becomes a continuous thread. In the requirements phase, security is explicit. Activities include rigorous threat modeling, identifying risks before coding. Security requirements documentation, like all user input, must be validated. And compliance reviews, ensuring GDPR, HEPAID, etc. are covered up front. Deliverables, clear security requirements, initial risk assessments. Tools like Microsoft Threat Modeling Tool or OS Threat Dragon help here.
So threat modeling happens right at the start. Ideally, yes. Thinking like an attacker before you design the defense. During design, we do thorough security architecture reviews. We apply secure design patterns, like privacy by design or least privilege. Deliverables include security architecture documents, attack surface analysis, pinpointing potential entry points.
Designing security in, not bolting it on.
That's the mantra. In implementation coding, we integrate secure coding standards. We run automated SAS scanning, static application security testing, to find flaws in the code as it's written, and use robust secrets management to avoid leaking keys or passwords. Deliverables, SAS reports, code review logs, often right in the developer's workflow.
Catching flaws immediately.
That's the key. Fast feedback. In the testing phase, the focus shifts to dedicated security testing, vulnerability assessments, and crucial penetration testing, pentest, simulating real-world attacks. Outputs are detailed pentest reports, vulnerability management plans, tracking fixes.
Trying to break it, basically.
Ethically, yes. Find the weaknesses before the bad guys do. For deployment, we implement secure deployment practices, like using hardened images, infrastructure hardening, disabling unnecessary services, and apply security baseline configurations consistently. Results: a hardened production environment, a ready incident response plan, and finally, in maintenance operations, security is continuous. Continuous monitoring of logs, applying security patches promptly, leveraging real-time threat intelligence. Deliverables, regular SOC reports, vulnerability feeds informing ongoing remediation. The overarching theme here is that testing is now left shifting, not just functional testing, but security testing moves earlier and earlier. The idea, as we said, is prevention is way better than cure. It's all about avoiding those last-minute surprises. Critical vulns found just before launch, or worse, after a breach that derail projects and cost a fortune.
Makes perfect sense. Proactive, not reactive. Okay, so we've got the SDLC and SSDLC firmly established. Now let's pivot to DevOps, which in its original form was itself a huge shift, wasn't it?
Oh, massive. A cultural revolution for many IT departments.
Yes. It was conceived primarily to dismantle organizational and procedural silos between dev and ops teams, right? Historically, they often had conflicting goals. Dev wants speed, ops wants stability.
The classic tension.
So DevOps aimed for a much faster, more agile software delivery lifecycle using CI/CD pipelines. The main driver was pure speed, getting features and fixes out super fast. But there's the catch. In this relentless pursuit of velocity, security often got, well, left behind. It was treated as an implicit requirement, not an explicit integral part of the process.
Yeah, it was often assumed or just hoped for.
It frequently remained a separate process, maybe managed by a dedicated security team acting as a gatekeeper right at the very end, just before deployment. And our sources highlight that this gatekeeper model totally undermined the agility DevOps was trying to achieve.
Right.
A dev cycle measured in days couldn't handle a security review that took weeks.
It became a massive bottleneck. Imagine sprinting towards the finish line and hitting a brick wall labeled security review.
Exactly. It created this persistent, frustrating, critical bottleneck, slowing everything down and, frankly, creating resentment towards security teams.
And this profound bottleneck is precisely what led to DevSecOps as the essential evolution. It's not just DevOps with security sprinkled on top. DevSecOps is defined as the evolution of DevOps that meticulously bakes security into every single phase of the secured software development lifecycle, SSDLC. It fundamentally transforms security. It's no longer a late-stage, often adversarial gatekeeper. It becomes a shared responsibility, actively embraced by DevOps and security teams working together. It's about building security in.
So integrating it fully, not just adding a check.
Fully integrated. And the key features that define this DevSecOps approach are: 1, shift-left security. We keep saying it, but it's core. Introduce security checks, vulnerability scanning, compliance reviews at the absolute earliest stages, planning, design, coding, prevent issues before they even start. 2, automation, huge reliance on tools. Automate code analysis, vulnerability scanning, dependency checks, compliance validation, makes security efficient, repeatable, scalable, minimizes manual toil and error. 3, collaboration, fosters that culture of shared responsibility. Breaking down silos, cross-functional communication. Security is everyone's job. 4, continuous monitoring. Security doesn't stop at deployment. Continuously monitor apps and infrastructure in production. Track threats, detect anomalies, respond to incidents after go live. 5, compliance is code. This is powerful. Automate regulatory checks and policy standards like no public S3 buckets using scripts and policy engines. Ensure compliance is built in and continuously verified, not a manual post-deployment nightmare.
Compliance is code. That sounds incredibly efficient.
It's a game changer for regulated industries.
That's a great summary of what makes DevSecOps so different. Maybe we can compare traditional DevOps and DevSecOps side by side to really hammer home the shift.
Good idea. Let's line them up.
Okay, so core focus. Traditional DevOps was primarily about speed and quality of delivery, getting features out fast and reliably.
Right. Velocity was king.
DevSecOps expands that significantly. Speed, quality, and security are co-equal priorities. Security is right up there. For security integration, DevOps often treated security as post-development, a separate review step.
Bolted on at the end, if at all sometimes.
Whereas DevSecOps embeds security throughout the entire SSDLC, from line 1 to production monitoring. Team composition. Traditional DevOps was Dev plus Ops.
The two main players.
DevSecOps explicitly adds security into the mix. They're integral collaborators from the start, often embedded in the teams. Dev plus Ops plus Sec. How about testing? DevOps focus mainly on functional and performance tests. Does it work? Is it fast?
Standard QA stuff.
DevSecOps includes those, but crucially adds security-specific testing. SAST, DAST, IST, dependency scanning, all as core parts of the automated pipeline. And finally, the tools. DevOps relied heavily on CI/CD pipelines, version control.
The core automation toolkit.
DevSecOps integrates those with specialized security scanners, compliance validation tools, runtime protection mechanisms, a much broader security-focused tool chain. The difference really seems night and day for security posture.
It's a fundamental shift in philosophy, tooling, and culture. And comparing traditional security approaches to DevSecOps really highlights that paradigm shift even further. Think about timing. Traditional security checks, often at the end of the SDLC, a final slow gate. DevSecOps, continuous, integrated throughout every stage. Planning, coding, testing, deployment, monitoring, always on. The core process, traditional, often linear, waterfall style, security as a separate phase. DevSecOps, iterative, cyclical, rapid feedback loops integrated into CI/CD. Responsibility, traditional, often the sole responsibility of a siloed security team. DevSecOps, explicitly a shared responsibility. Everyone owns it.
That shared responsibility seems key.
Absolutely fundamental. The primary focus. Old school, often network perimeter and infrastructure, firewall segmentation, DevSecOps, holistic security. The application, its dependencies, the infrastructure, the pipeline itself, everything. Tooling, traditional, often manual reviews, disconnected scanning tools run ad hoc. DevSecOps, highly automated, integrated toolchain embedded in the pipeline. Consistent, automatic checks, pace and velocity. Traditional security gates created significant bottlenecks, delaying releases. DevSecOps, by integrating security, actually enables and accelerates high-velocity secure delivery. Security becomes an enabler, not a blocker. Outcome. Traditional often led to reactive remediation of late-found vulns, costly, stressful. DevSecOps focuses on proactive identification and remediation early on. Less cost, less risk. Culture. Historically, security was sometimes seen as the antagonistic Department of No. DevSecOps explicitly fosters a collaborative culture. Security is a shared goal, an enabler of quality and innovation. It's a mindset shift.
From gatekeeper to partner.
Exactly. That's the ideal.
Okay, to bring this down to earth, let's quickly run through the 7 key stages of DevSecOps activities, showing exactly how security gets woven in, practically speaking. 1. Plan. Teams don't just define functional requirements, they define security requirements with the same rigor. Data encryption needs, access control, compliance mandates, all defined up front. Security is a first-class citizen. 2. Code. Developers adhere to secure coding standards. They actively prevent things like SQL injection or cross-site scripting, XSS. They might use IDE plugins for real-time feedback.
Secure coding becomes part of the craft. 3. Build and deploy. The CI pipeline orchestrates automated security scans on code and dependencies as soon as code is committed. Checks for exposed secrets, vulnerable libraries. Build fails if insecure code is detected.
Stopping bad code early. 4. Test. The pipeline runs tests simulating real-world attacks. Dynamic analysis finds runtime vulnerabilities, authentication bypasses, broken access controls, trying to break it securely. 5. Release. Before official release, the packaged app, like a Docker image, is scanned for known vulnerabilities in its layers and system libraries. Final check on the artifact itself. 6. Deploy. Configuration validation. After deployment, automated checks confirm the live environment's configuration hasn't drifted from the secure state defined in infrastructure as code, IAC, prevents dangerous misconfigurations.
Ensures consistency between code and reality. 7. Operate and monitor. In production, constant surveillance, real-time log analysis, automated patching, monitoring with tools like WEFs, RISP, SIEM systems, real-time defense, and incident response.
It really is a continuous interlocked cycle. Security is ingrained at every single turn. It transformed what used to be a siloed afterthought into an integral automated part of the software's entire journey.
Right. And building directly on DevSecOps, the engine that makes it all work is the CI/CD CS pipeline. Let's break down its components, starting with continuous integration, CI. So CI automates integrating code changes from multiple contributors into a shared repository. Imagine a big project, dozens of developers, maybe different teams, time zones. CI makes sure their code merges smoothly. It prevents that integration hell nightmare where merging code took days of resolving conflicts.
Keeping everyone in sync automatically.
Exactly. The CI process involves several key automated steps. Code commit. Developers push small, frequent updates to version control like Git. Automated build. Each push triggers an automated compilation of the code into something executable, a JRR file, a Docker image, whatever. Automated testing. Right after a successful build, automated tests run unit tests for individual bits, integration tests for how they interact. Feedback loop. This is critical. If any build or test fails, coding error, dependency conflict, maybe even a new security flaw flagged by a tool, immediate alerts go to the team via Slack, email, dashboard, whatever works.
So they find out instantly.
Within minutes or hours, usually, when it's still cheap and easy to fix. The main goals of CI: catch bugs and integration issues super early, ensure the code base is always stable, always working, and drastically cut down those integration conflicts that used to kill productivity. It's about maintaining a healthy code base continuously.
Okay, so once that code is continuously integrated and validated by CI, the next step is continuous deployment, or continuous delivery CD. CD automates deploying that validated code to various environments, ultimately getting it to production, right?
That's the idea. Every change passing CI is automatically released or made ready for release. It eliminates those manual, often error-prone deployment processes.
And the key components of CD include an artifact repository, a secure place to store those tested, validated builds, like Docker images, binaries, ready for deployment anywhere, environment deployment, automating deployment to different stages staging, which mirrors production, and then maybe automatically to production itself. Ensures consistency, same deployment process everywhere.
Ideally, yes.
What else? Automated tests keep running in these deployed environments. End-to-end tests simulating user workflows, performance, and load tests for scaling. And critically, a solid rollback mechanism, pre-configured, ready to automatically revert a bad deployment back to the last known good version, maybe using techniques like blue-green deployments or canary releases.
Essential for minimizing user impact during releases. Zero downtime is the goal.
And the goals of CD: deliver features and fixes faster, minimize deployment risks through automation, and ensure those zero downtime releases so users get seamless updates. Huge win for user experience and business continuity.
Now, what really connects CI and CD to secure software engineering and makes them core to DevSecOps is continuous security, or CS. This component explicitly integrates security checks throughout that entire CI/CD pipeline. It fully embodies the shift-left idea by finding vulnerabilities at the earliest possible moment. CS uses several key techniques, each catching different types of flaws. Static application security testing, SAST, we mentioned this. White box scanning of source code, binaries, bytecode before the app runs, like a security spell checker for code logic. Tools like SonarQube, Checkmarks, Fortify, dynamic application security testing, DEST. The contrast, black box testing of a running application, simulates attacks against the live interface or APIs. Tools like OWASP, Zappy, Burp Suite.
So SAST looks at the code, DAST looks at the running app.
Exactly. Different perspectives, find different things. Dependency scanning, SCA, crucial today. Checks third-party libraries for known vulnerabilities, CVEs. Think Log4j, Heartbleed. Finds risks in your software supply chain. Tools like SNCC, Dependabot. Secrets detection specifically looks for accidentally exposed credentials, API keys, passwords hard-coded in source code or committed to Git. Tools like Git Guardian. Compliance checks. Automated checks ensuring the software and infrastructure meet internal policies or external regulations, GDPR, HIPAA, PCI DSS. Compliance as code. The main goals of continuous security: identify flaws early, ideally during development, maintain continuous compliance, and drastically cut the remediation costs of fixing vulns found later. It's proactive defense, not reactive panic.
Okay, let's bring all these pieces, CI, CD, CS, together. Walk us through a typical integrated pipeline flow. Visualize it as that seamless, endless loop of improvement and security. It starts in the CI phase. 1. Code commit. Developer pushes code to Git. 2. Build. Code gets compiled automatically. 3. Automated tests. Unit and integration tests run. Functional checks pass. Now, the CS phase integrates seamlessly, often right after or alongside functional tests. 1. SAST scans the new code for static flaws like SQL injection points. 2. Dependency scan, SEA, checks third-party libraries for known CVEs, flags outdated or vulnerable ones. 3. Secrets detection scans for exposed credentials, blocks the commit or alerts if found. And crucially, if any of these security checks fail, the pipeline halts. The team gets alerted immediately. Insecure code doesn't proceed.
That's the automated gate in action.
If all checks functional and security pass, we move to the CD phase. 1. Artifact storage. The validated artifact, see Docker image, is securely uploaded to a repository like Docker Hub or Nexus. It's a trusted build. 2. Staging deployment. It's automatically deployed to a production-like staging environment. Here, DAST scans the running application, simulating attacks. End-to-end and performance tests also run here.
Final validation before the real deal. 3. Manual approval, optional. May be needed for regulatory reasons or sensitive releases. 4. Auto-deploy to production. Often, for frequent updates, it deploys automatically. Final smoke tests and health checks confirm everything's okay live.
And wrapping this whole thing is a continuous feedback loop. Failures at any stage trigger alerts. Metrics from production monitoring, feedback into development. This restarts the cycle plan: code, test, secure, learn. Constantly improving, constantly adapting. It truly is an endless loop.
That's the power of the integrated pipeline: continuous improvement, continuous security. Right. So with that pipeline structure in mind, let's zoom in on the specific tools and technologies that make this integrated secure software engineering actually happen. For secure coding and design, a critical proactive practice is threat modeling. We touched on this. It's a structured way to identify risks early, during design, before coding starts. Popular tools: OWASP Threat Dragon helps visualize attack paths. Microsoft Threat Modeling Tool is another. More advanced ones like Arius Risk integrate threat intelligence feeds.
Thinking like an attacker early on.
Exactly. And a crucial standard, especially for web apps, is the OWASP ASVS Application Security Verification Standard. It's not a tool, but a comprehensive framework. It gives you a basis for testing security controls and provides developers with clear, tiered requirements for secure development. Helps you measure the trustworthiness of an app and to enforce secure coding while developers work. Secure templates and IDE plugins are invaluable. Tools like SonarLint plug right into the developer's IDE, giving real-time feedback on potential security flaws or code quality issues as they type. SNCC IDE does similar things for open-source vulnerability.
Security advice right in the editor.
Makes it much easier to catch things immediately. And often, these tools and standards are laser-focused on preventing the notorious OWASP top 10 web application security risks. It's worth quickly recapping what those are because they're so common.
Yeah, good idea. What are we looking out for?
Okay, briefly. Broken access control. Users getting access to stuff they shouldn't, viewing someone else's data using admin functions, cryptographic failures, weak encryption, storing passwords badly, using outdated crypto, leaving sensitive data exposed, SQL injection, injecting malicious SQL code via input fields to mess with your database. Super common, very dangerous. Insecure design. Fundamental design flaws, not just coding mistakes, like forgetting rate limiting, making brute force attacks easy, security misconfiguration, incorrect settings on servers, apps, and networks, default passwords, open ports, revealing error messages. Alarmingly common.
Simple mistakes, big impact.
Huge impact. Vulnerable, outdated components. Using old libraries or frameworks with known exploits like Log4j. Attackers love scanning for these. Identification authentication failures. Weak passwords. Bad session management, allowing login brute forcing. Software data integrity failures. Tampering with software updates, critical data, or the CI/CD pipeline itself. Injecting malicious code. Security logging monitoring failures. Not logging enough, not monitoring, not alerting. Means you can't detect or respond to attacks effectively. Blindness. Server-side request forgery, SSRF. Tricking the web app into making requests to internal systems or external resources it shouldn't access. These are the kinds of things these tools and secure practices aim to prevent and detect systematically.
That OWASP top 10 list is sobering. These are the real battlegrounds. So how do we actually find these things automatically in a fast DevSecOps world? That's where automated security testing comes in, right? It's multifaceted. Let's break down the different types again, clarifying purpose and where they fit. First, SAST, static application security testing. Type, white box. Looks inside the code. Source, binary bytecode without running it. Machine-based code review. When? Early, during coding development. In the IDE, pre-build checks. Analyzes. Source code, binaries, bytecode. Scope. Finds logic flaws, hard-coded secrets, injection risk, SQL, XSS, code quality issues that cause vulnerabilities. Strengths. Finds flaws super early, shift left, full code visibility, no running app needed. Fast feedback for devs. Limitations. Can have high false positives. Misses runtime issues. Misconfigs, off flaws. Language tool dependent. Tools. SonarCube checkmarks fortify your big names. Okay, next. SEA software composition analysis. Type. Identifies and manages open source components, libraries, frameworks. Understands your software supply chain. When? During build CI phase, as dependencies are pulled in. Analyzes. Open source libraries, NPM, Maven, pip packages. Scope. Finds known vulnerabilities, any dependencies. Log4j, Heartbleed. Checks licenses. Finds outdated libraries. Crucial for supply chain security. Strengths. Essential today. Automated patch suggestions. Prevents inheriting vulns. Limitations. Can't find flaws in your custom code. Limited to known vulnerabilities in public databases. Won't find 0Ds in your code. Tools. SNCC, Dependabot, GitHub, WhiteSource are key here.
SCA is absolutely non-negotiable these days with how much open source we all use.
Totally. Okay, then DAS Dynamic Application Security Testing. Type, black box. Analyzes a running application from the outside, simulating attacks. Doesn't need source code access. When? Later. During testing QA phase, maybe post-deployment and staging. Analyzes HTTP PDI requests, web interfaces, runtime behavior. How does it respond to malicious input? Scope. Finds runtime vulns, configuration errors, exposed admin panels, authentication flaws, session issues, API gaps, things SAST might miss. Strengths. Real-world attack simulation. Finds runtime-specific issues. No source code needed. Limitations. Needs a running app. Scans can be slow. Blind to source code context. Doesn't pinpoint the line of code. Hard to simulate all complex attacks. Might miss parts not discoverable via crawling. Tools. OWASP, BZAP, Burp Suite, Akinetic, SQL Map are common, and newer but increasingly vital, especially for cloud. IC security infrastructure is code scanning. Type. analyzes infrastructure code itself, Terraform, CloudFormation, Kubernetes manifest, Docker files. When? During CI/CD in the infrastructure provisioning phase before deployment. Analyzes IAC templates, scope.
Finds cloud misconfigs, public S3s, over-primitive IAM roles, exposed storage, non-compliant resources, strengths, prevents toxic cloud environments before they happen, enforces compliance pre-deployment, codifies security policies for infrastructure, limitations, limited to the infrastructure layer defined in code, can miss runtime drift if manual changes happen later, can have false negatives and complex templates. Tools, Checkoff, Tarascan, Bridgecrew are popular.
Preventing cloud misconfigurations is huge. So many breaches start there.
Definitely seems like it. Okay, and finally, IST interactive application security testing. Trying to bridge SAST and DAST. Type, hybrid. Runs inside the app server, like an agent. Evaluates code like SAST, but identifies issues during runtime interaction, like DAST. Observes behavior from within. Strength. Aims for fewer false positives than SAST. Deeper code visibility than DAST at runtime. Often gives more precise locations line of code for runtime issues. So it's clear each tool has its purpose. SAST finds code flaws early. SCH checks dependencies. DAST probes the running app. ISE scans infrastructure definitions. You need a mix, right? Integrated across the SSDLC, SAST to CA during implementation, DAST during testing, ISE during deployment.
Exactly. It's about layering these automated checks throughout the pipeline for comprehensive coverage. No single tool finds everything. Okay, so once the software is deployed, the focus shifts again, from finding vulnerabilities to actively blocking attacks in real time. This is where runtime protection comes in. A key technology here is RASP, Runtime Application Self-Protection. Definition. Think of RASP as an evolution beyond SAST/DAST. Its core focus is intelligently blocking attacks in production in real time. Mechanism. RASP tools integrate directly with the application, like an agent or library. They continuously analyze traffic, monitor app behavior, even user interactions at runtime. If they detect an attack, like SQL injection, they can block that specific request without taking the whole app down. The application essentially self-protects.
So it's like a built-in bodyguard for the application.
That's a good analogy. It's context-aware defense from within. When used. Crucially, RASP is deployed after production release. Its job is real-time defense and protection, not testing. It ensures resilience in the live, hostile environment. Tools include contrast security, Imperva real-time RASP. Another vital area, especially with cloud-native stuff, is container security. Continuously scanning Docker and Kubernetes images before deployment, checking for misconfigurations, known vulnerabilities in the image layers, adherence to best practices. Tools like Aqua Security, Prisma Cloud specialize in this, ensuring the very building blocks of your modern apps are secure. These runtime protections are that critical last line of defense.
Okay, shifting from protecting individual apps to ensuring the whole system follows consistent rules. Continuous compliance. You mentioned this, taking rules like no public S3 buckets and enforcing them automatically everywhere.
Yes, codifying and automating compliance checks.
And a central player here is Open Policy Agent, or OPA. You said it's a general-purpose policy engine.
Exactly. OPA's power is unifying policy enforcement across the entire stack. Infrastructure, AWS, Azure, APIs, microservices, CI/CD pipelines, even data systems. One engine, consistent rules.
How does that work? Policy is code.
Right. You write policies in Rego, OPA's declarative language. Store these policies as code and Git versioned, reviewed. OPA can run decentralized, right next to the service it protects. Sidecar, daemon, library, making fast local decisions. You get unified control over diverse policies, and it uses dynamic context, real-time data like user roles, request attributes, cloud tags to make granular decisions.
So a service asks OPA, can I do this? And OPA checks the rules.
Precisely. Service sends a query. AG, can user X do Y? OPA evaluates policies against the query, and maybe external data returns a loudiny. Simple but powerful.
And there's an ecosystem around it.
Growing fast. Gatekeeper is a Kubernetes admission controller using OPA to enforce policies before resources are created in the cluster. ConfTest lets you test config files, Terraform, YAML, against OPA policies before deployment. Shifts ISE compliance left. Styra DAS offers enterprise management. You see OPA integrated throughout the pipeline ConfTest during CLAN, gatekeepers in Kubernetes at deploy time, continuous compliance from code to cloud. And once everything's live and protected, the final continuous layer is threat monitoring and response. This is where SIEM, Security Information and Event Management tools, become the eyes and ears. The goal of SIEM: aggregate, analyze, manage vast amounts of security data from everywhere: servers, apps, firewalls, identity systems, security tools. Without SIEM, it's just overwhelming noise.
Bringing all the signals together.
Exactly. Their core purposes are indispensable: log management, Collect, consolidate, normalize petabytes of logs. Make it searchable. Real-time monitoring and alerting. Continuously analyze logs in real time. Use rules, machine learning to spot suspicious activity, anomalies, threats. Generate immediate alerts. Always on detection. Threat detection. Use correlation rules, analytics to find attack patterns that individual alerts might miss. Incident response. Central platform to investigate incidents, trace attacks, identify affected systems, coordinate remediation. The cyber defense war room. Compliance reporting. Provide detailed reports on user activity, security events, audit trails. Makes audits much easier. Popular tools. Splunk is a big commercial player. The ELK stack, Elasticsearch, Logstash, Kibana, is a powerful open source option. These tools provide that crucial holistic visibility, turning raw data into actionable security intelligence.
Okay, that's a ton of powerful concepts and tools. How does an organization actually implement all of this? It sounds like a massive undertaking. Our sources provide a clear, 5-step roadmap for DevSecOps adoption. It's a journey, right? Not an overnight thing.
Definitely a journey. Incremental steps are key.
Step 1, assess. First, audit your existing pipelines. Where are the security gaps? What tools are missing? What manual processes or bottlenecks? Get that baseline understanding of your current posture. You can't fix what you don't know is broken.
Absolutely crucial starting point. Honesty about where you are.
Step 2, automate. Once you know the gaps, automate. Integrate SaaS SCA into CI. Bake IAC scans into CD. Make security checks automatic, consistent, scalable. Reduce manual work and errors. Step 3, educate. Tools aren't enough. Train developers on secure coding, OWASP top 10. But also teach the attacker's mindset. Use capture the flag exercises, fix-a-thons. Build security empathy. Make it part of their craft.
Culture change starts with understanding.
Step 4, monitor. Once deployed, use RASP and SIEM for continuous surveillance and runtime threat detection. Catch issues that emerge live, your early warning system. Step 5, iterate. DevSecOps is never done. Continuously refine policies, tools, processes using feedback from monitoring, incidents, vulnerability reports, constant learning, adaptation, refinement. That's the hallmark of maturity.
Continuous improvement is built into the name, and this journey follows a maturity model. Organizations typically move from ad hoc, reactive, chaotic security to defined, documented processes, maybe manual, then integrated, more formalized security in the pipeline, maybe not fully auto, then automated, extensive toolchain integration, continuous checks, and finally optimized, where security is seamless, self-healing, continuously improving, proactively adaptive, almost invisible because it's so well integrated.
A clear progression to aim for. So once you're on this journey, how do you know if you're succeeding? We need key performance indicators, KPIs, and metrics. Our sources highlight 2 key sets. First, the DORI metrics, industry standard for overall software delivery performance, directly applicable to DevSecOps. 1, deployment frequency. How often do you successfully release to production? Measure. Count successful deployments per team per time period. Value. Faster time to market, quicker patching.
Higher frequency is generally better, assuming stability. 2, lead time for changes. Time from code, commit to production deployment. Measures pipeline efficiency. Measure. Median time, commit to deploy. Value. Increased efficiency, faster response to market feedback, rapid security patching. 3, mean time to restore, MTTR. How long to restore service after an incident failure? Measure.
Yeah.
Time from detection to full restoration. Value. Better reliability, less revenue loss, protects brand. DevSecOps helps automate recovery. 4, change failure rate. Percentage of deployments causing service degradation, needing hotfix rollback. Measure. Failed deployments. Total deployments, 100. Value. Higher quality, less rework, builds user trust. DevSecOps aims to drive this near zero. These 4 give a great high-level view of delivery health, including security's impact.
Then we have security-specific KPIs for a more granular view. 1, mean time to detect, MTTD. Average time to discover a security vulnerability, measure. Time from vul introduction to detection, value. Reduces the risk window, lowers breach probability. Shows proactive security.
Shorter is much better here. 2, vulnerability remediation rate. Speed at which identified vulns are fixed. Measure. Median age of open vulns by severity. Value. Proactive risk management reduces long-term security debt. Shows responsiveness. 3, security burn down. Chart tracking open, unresolved security issues over time. Measure. Plot active vulns week by week. Line should go down. Value. Visible progress on security debt reduction. Great communication tool. 4, proactive compliance percentage. Percent of security compliance controls met automatically by the pipeline. Measure. Percent automated compliance checks passed in CI/CD. value, ensures consistent adherence, reduces audit overhead, enhances trust, making compliance provable and continuous.
And our sources also briefly mention cost per defect rework and customer satisfaction, CSD. These directly link security effectiveness to the bottom line and brand loyalty. Fewer security defects means lower costs and happier, safer customers.
Absolutely. Security directly impacts business outcomes, but it's absolutely vital to remember all the tools, processes, metrics. They aren't enough alone. A strong, supportive culture is paramount in DevSecOps. Without the right mindset, the tech falters. It starts with leadership's role. Execs must actively champion the vision, secure resources, budget, tools, training. Consistently communicate security as a core value, co-equal with speed. Celebrate security wins. Set the tone.
Tone from the top is crucial.
Always. Then there's education and enablement. Continuous learning, not one-off training. Secure coding workshops, access to security expertise, champions, immersive learning like capture the flag, fix-a-thons, building understanding and capability. Collaboration and communication are key to breaking silos. Cross-functional teams, including security, shared communication channels, and crucially, blameless post-mortems after incidents. Focus on learning and system improvement, not blame. Fosters psychological safety.
Learning from mistakes without fear.
Essential. Finally, building empowerment and trust. Empower engineers to make secure decisions. Foster psychological safety to try things, even fail occasionally. Security leadership should provide guardrails, not gates, flexible controls, automated checks that guide, not rigid blockers that frustrate. Enable security, don't just enforce it.
Guiding, not blocking. A much better approach. Okay, let's tie it all together. How do these big three CI, CD, and CS individually and collectively impact each major phase of the SDLC we outlined, creating that truly integrated workflow where the rubber meets the road? In the planning and requirements phase, CI impact, maybe less direct here, but can automate validation of requirement artifacts against acceptance criteria, measures traceability coverage. CD impact, influences planning by pushing for early definition of deployment targets, cloud on-prem, measuring environment parity needs, planning for smooth deployment later. CS impact, huge shift left impact, auto-checks requirements against standards like OWASP SES, uses tools like Threat Dragon for early threat modeling, measures percent of security requirements automated, security from thought one.
Embedding security in the definition phase.
Moving to the design phase, CI impact, can automate validation of architectural decisions via architecture tests or design pattern checks in the build, ensure design consistency. CD impact, drives infrastructure as code, IAC, designed for reproducibility, ensures the design facilitates automated, consistent environment provisioning. CS impact, enforces secure design patterns, zero trust, uses tools like Chekhov-Taraskin to scan IAC definitions in the design phase, measures design flaws detected before coding.
Catching architectural security flaws early.
During implementation, coding, CI impact, the core value prop, auto builds tests on every commit, immediate feedback on quality functionality. CD impact, creates immutable artifacts, Docker images, provisions, consistent test environments, build once, deploy consistently. CS impact, real-time SEMP-SA, secrets detection, SCA analysis during coding using SNCC, SonarQube, Git Guardian, immediate feedback in the IDE, measures vulnerability density, security checks happening as code is written.
That's the ideal feedback loop.
In the testing phase, CI impact, enables robust automated regression testing, ensures new features batches don't break things. CD impact, automated deployment to various test environments, QA, staging, UAT, for comprehensive validation. CS impact, rigorous DAS scanning, OWASP, LDAP, ZAPI, Burp Suite, IS scanning, fuzzing techniques applied here, measures percent WASP top 10 coverage by tests.
Probing the running application for runtime flaws.
For deployment, CI impact, final build validation before a release candidate is approved. CD impact, enables automated zero downtime deployments, Kubernetes Istio, facilitates auto rollback, measures deployment frequency, rollback success. CS impact, runtime protection activation, WRASP. Configuration scanning ensures deployed environment matches secure IAC baseline, measures time to mitigate new threats, securing the release in the live environment.
Protecting the final frontier.
And finally, in operations, post-deployment, CI impact, triggers hotfix pipelines for urgent security patches or bug fixes in production. Rapid controlled remediation, CD impact, supports feature flag management, auto-scaling, automated recovery using monitoring like Prometheus. CS impact, continuous RASP protection, active threat protection, auto-patching via SIEM CSPM solutions, measures MTTR for security incidents. How fast can we recover securely?
Keeping it secure and resilient in the wild.
This detailed walkthrough really highlights how CI, CD, and CS aren't just bolted onto the SDLC, they're fundamentally woven into every stage. It creates this powerful, continuously secure, highly responsive ecosystem. It really is a sophisticated choreography.
It truly is. When done right, it's seamless. Hashtag outro. So we've covered a lot of ground. We journeyed from that foundational 8-step process of traditional software engineering all the way to the sophisticated, integrated approaches of SSDLC, DevSecOps, and the CI/CD CS pipeline. What should be crystal clear now is that security is absolutely no longer an afterthought. It's an intrinsic, inseparable part of the software's very DNA. It's meticulously driven by critical business needs, the relentless evolution of threats, and those stringent regulatory demands we talked about. It's a continuous, proactive effort.
Absolutely. And hopefully you, our listener, now have a far deeper, more nuanced understanding of these sophisticated processes, the specialized tools, the collaborative cultures, everything that ensures the software you rely on every single day isn't just functional, but robustly secure. It's really about that unseen rigor, isn't it? That invisible architecture defense, the constant vigilance and automation that keeps your digital life safe, your data protected, and your online experiences smooth and trustworthy. It's a complex, fascinating field that genuinely touches everyone.
And as we wrap up this deep dive, let's leave you with a provocative thought, something building on what our sources hinted at regarding the future. We've explored these traditional yet constantly evolving best practices for secure software, but the next frontier involves the, well, explosive potential of agentic AI and generative AI revolutionizing how software is built, potentially allowing software to, in essence, write large parts of itself, maybe even entire applications. So the question to ponder is, what profound implications might this have for secure software engineering? How will these foundational principles, which currently rely heavily on human understanding, review, and oversight, adapt to a world where software might autonomously generate new code that could potentially be vulnerable in ways we haven't even conceived of yet?
Wow.
It's a fascinating challenge, isn't it? How do we maintain security when the creator itself might be artificial intelligence? Something to think about.